All right, so I want to look at how to use the calculator to find your probabilities, okay? And even if you have the 83, you can still do this. It just doesn't give you the handy little menu, all right? So you'll just have to remember what order to type things in, all right? So it says, I'm going to use the example that you can see at the top there. If 20% of people get enough sleep and you survey 20 people, we're dealing with the binomial expansion 0.2 plus 0.8 to the 20th power. Okay? So we have this statistic, 20% of people get enough sleep. All right? And we picked 20 people at random. Now, again, I can assume that this is going to be independent because we're talking about like over the course of the country or maybe the world, depending on what this survey was from. Okay? So, me taking 20 people out of the, 300 million that are in our country, is it 300 million? Ish, somewhere around there. Okay? That's not going to change our probability at all. Okay? So what I would do at this point is I'm going to use one of two functions on the calculator. Okay? And you'll see over on the right hand side, you see this binom PDF and binom CDF. Okay? Now let me show you how to get there on the calculator. Alright? I'm going to insert video. Okay.
Hi, Mr. Hicks.
Hello. All right. So, if I want to get to that binomial PDF or binomial CDF, you'll see right above the VARS, right above the variables, you see DISTR. That stands for distributions. Okay? That is the menu where you'll find everything related to the different distributions that we can do. All right, so if I hit second distribution, you'll see here normal on the first three. Okay, we will use two of those three very soon. Okay, there's a T distribution. There's a chi-squared distribution, number 7 and 8. I think F is that the Fourier or something like that? There's a Poisson. All right, but what we want is binomial. Okay? It's French for fish. So, but there's a distribution called the fish distribution. So, I forget what it looks like. I'm assuming probably. But anyways, okay. So here's the difference, okay? And this is very, very important that you understand this. Binomial PDF, that's the binomial probability distribution. What that will give you is the probability of getting exactly a certain number of outcomes. Okay? So each of those individual terms, if you want one of those terms, this is what you want to find. Okay? Now, the X value is very important, okay? You've got to think about what order your terms are in, okay? Up above here, we made it 0.2. So those are the people who are getting enough sleep. So we need to be careful when we read the problem that we're answering the question properly, okay? We go out of here. I'll move this over. Okay? The CDF we're going to get to in a second. That gives us a range, all right? So when I type in binomial PDF, it gives me this little menu of trials. What's your P? The P is the probability of what you want to find. Okay? We want to find the probability that X equals 7. All right? So what does this mean? This is the probability of getting exactly 7 people out of the 20 who actually do get enough sleep. Okay? So I use binomial PDF. I plug in 20 for the number of trials because that's how many people I surveyed. Okay? I put in a 0.2 because that's the probability of finding someone who actually did get enough sleep. And then I type in 7 because that's how many people I wanted to have enough sleep. Okay?
Which 7?
If you have the 83, the TI-83, all you do is you just type it in that order, N, P, and X, separated by commas. The comma is right next to the left parenthesis. So you'll type in 20, comma, 0.2, comma, 7.
Wait, why would you type that?
She's got a TI-83, so it doesn't give her the little menu like you guys get over here, the helps. Okay? All right, so when you do that, it ends up being binomial PDF 20.27, and what do you get?
0.054. 0.055. Yes.
0.05, let's do 3 sig figs.
0.054.
545? Okay. So we have just over or almost 5.5%, so 5.45% chance of getting 7 people who got enough sleep. Okay? By the way, think. Okay? Think about whether your answer makes sense. 7 out of 20, that's 35% of the people. If our chances are only 20%, then it's likely that our probability is going to be lower, right? Okay, so if you accidentally type this in wrong and you put the 0.8 in for P and you got something like, 68% or something like that, that should make you think, all right? So that's how we use the binomial PDF. Now, what if I wanted the probability of getting less than or equal to 7 people who got enough sleep?
CDF.
That's where the binomial CDF comes in. Okay? Now, this is one of the few instances I think where the n-spire is kind of nice. The n-spire will allow you to put between 2 values on your binomial CDF. So notice down here, the binomial CDF goes between x and y, so you could put 0 and 7. Okay? Now for this problem, it doesn't make any difference because the TI-84 automatically will do it from 0 up to whatever you put in for x. Okay? So if I typed in the same thing I did up here, but I had binomial CDF instead of PDF, it'll give me the probability of getting nobody with enough sleep, 1 person with enough sleep, 2 people with enough sleep, all the way up to 7 people with enough sleep. What? Same thing. If I type this in with the binomial CDF instead, it'll give me the probability from 0 up to 7. Okay? So yours will look like this. Binomial CDF 20.2 and 7. Okay? Huh? 0.967?
Yeah.
Is that what anyone else got?
9.968.
Okay, what are the decimals there? 0.9678. Okay, so you'll round that to 0.968 if we're doing 3 significant figures there. Okay? All right, so we have a very good chance of getting 7 or fewer people who actually got enough sleep. Okay? Now, question here. What's the probability of getting more than 7 people who got enough sleep?
It's the number minus 7.
Yeah, it's the number, it's this taken away from 1. Okay? So 0.032.
So this is
So-
exactly what the correlation coefficient, because the closer it is to 1.
No, it's different than correlation. The closer it is to 1, the more certain we are that this is going to happen. Okay? But all of these probabilities are going to add up to 1. Because 0.2 plus 0.8 to the 20th power, 0.2 plus 0.8 is 1. 1 to the 20th power is 1. So I know they're all going to add up to 1 in the end. That's why if I wanted the probability of getting more than 7, I would just subtract this from 1. Okay? Now, let me give you one more example that's not written on here, because this is where it can be a little bit challenging, even using your calculator. All right? What is the probability of getting between anywhere from 5 to 10 people who got enough sleep?
And just do it for 5 and then do it for 10.
Do what?
Never mind.
Well, how do you do the ranges?
That's where the end spire is nice, because the end spire lets you put in a between this and this.
Well, you know what?
Okay?
You do it for 5 because it's
The end
0 to
spire
5.
isn't allowed
And then would
anywhere
you do it for
but
10
not
but then
5.
subtract them?
Oh, that's a good idea, okay?
Does that work?
Did you guys hear what Matthew just said? He said if you do it, let's think about this. I'm just gonna do a quick little picture here. Here's the probability of 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, all the way up to 20. Okay? So he said if you find the binomial PDF up to 5, and then find the binomial PDF up to 10, and subtract, that should give it to you. Now, is that correct?
No, because you have to include 5. And then if you subtracted those, then you would have between 6 and 10.
So you just do
4, you'd be like,
yeah.
4.
Yes, we would do 4. You do the binomial PDF up to 4. I have equal to. I'll be equal to. And then we have this, okay? So look, if I do binomial PDF, up to 10, or sorry, CDF, should have said CDF. By the way, it's called CDF because it's cumulative distribution function. It's cumulative. So it goes from 0 up to 10 if I put in a 20, a 0.2, and a 10. But then I need to subtract the 0 to 4 that I don't want to include. Okay? So minus binomial CDF 20, 0.2, and 4. Okay? Now you might be thinking, well, that's really kind of tedious. That's, annoying. Well, it is, but it's a lot less tedious than having to figure out exactly what 5, 6, 7, 8, 9, and 10 are and add them all up.
Right.
Okay? However,
No.
there is an alternative way,
Okay.
which may be a little bit more intuitive for you on the calculator. Now, this is one where the 83 is terrible, so I would not do it this way on the 83. I would just do it exactly how I just showed you. Okay?
When I pressed enter after I did that whole thing, it just said quick go
that means you have some kind of an error in how you typed it in. Okay. So the other alternative is what I just talked about. Finding the probability of exactly 5, exactly 6, exactly 7, exactly 8, exactly 9, exactly 10, and adding them all up. Okay? How do I find the probability of getting exactly a certain number?
PDF.
PDF. Okay? So guess what I'm going to do? If I put binomial PDF and I use 20.2 and then X, guess what I could do with that? Watch this, guys, because this is super helpful. All right? I'm putting in an X. And you say, well, why are you putting in an X? Because if I go to math and I scroll down, I have summation. And on the TI-84, you can do the sigma notation and do X equals, and we want to go from 0, or I'm sorry, we don't want to go from 0, we want from 5 to 10. So I'm starting at 5 and I'm ending at 10.
Oh my gosh.
See, it seems kind of easier, but it also seems not the same.
Yeah, I feel like this is way harder actually.
So the key is, here's two options. Whichever one makes sense to you, use it.
It's actually faster though.
Okay, it's a little bit faster. But if that picture I drew up there makes sense to you, and it makes sense to do binomial CDF minus binomial CDF, then go for it. If using the sigma notation makes more sense to you, then go for that. Okay? This is one thing with your calculators, guys. You've got to just try stuff and play with it and see what works best for you. Because there's usually more than one way to do this stuff. Okay? All right, so regardless of which way we do this, we're going to end up getting the percent or getting the value 0.36978. So 698, or we could say to 3 significant figures, it would be 0.370. Okay? Now what that is saying is that if we surveyed those 20 people, we have about a 37% chance of getting between 5 and 10 of those people to have had enough sleep.
I have no idea.
That between 5 and 10 of them had enough sleep. Okay? So that's what that's saying. Okay, guys, so let's work our way through this one to make sure that you guys are on the right track here, okay? First of all, if you don't remember how to do the binomial expansion, that's something that you need to review, okay? Not just for this, but also you will have to expand like polynomial binomials as well. Here we're doing the binomial expansion in order to find probabilities, okay? So I want to take our time going through this and make sure that you understand exactly what is going on here, okay? So for part A, expand 3/4 plus 1/4 to the 5th power, okay? Well, guys, what does 3/4 plus 1/4 to the 5th power equal?
1.
1 to the 5th power.
1 to the 5th power, which is 1, all right? That means this is a valid probability distribution, right? They all are going to add up to 1, all the different outcomes, okay? So what we have here, if you remember our binomial expansion, we had to get the combinations with Pascal's triangle, right? So you had 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1.
Can we do the what was the thing she did last year? It was like the
actual
something,
combination?
choose something, yeah.
Yeah.
Can we do that?
Yes,
Okay.
that works. And actually, we will be using that if you're finding just one individual one. Okay? We're expanding the whole thing, so we might as well go ahead. You had 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. Where do I need to stop?
Sorry, 1, 5, 10.
5, 1.
Okay, why am I stopping here? Because it's to the 5th power. Okay, it's to the 5th power. So I'm going to stop on the 5th row. That's going to give me all of my coefficients. So I have 1 plus 5 plus 10 plus 10 plus 5 plus 1. Okay? Then we have our two different terms. We've got the term 3/4. Okay? And if you recall from our expansion, the first term has that 3/4 to the highest power, so to the 5th power. And then we count down 3/4 to the 4th, 3/4 to the 3rd, 3/4 squared, 3/4 to the 1st power, and then 3/4 to the 0, so there's nothing on the last term.
How do you get like the numbers 1, 2, 1, 1, 2? I never knew.
That's Pascal's triangle. Were you in pre-cal honors?
I learned it in pre.
I didn't go here when I took the calculus last year, so I went to the school.
Okay. So this is Pascal's triangle. I can show you in I can show you some stuff to help you review this part. Okay. All right. So then we have this second term, which is 1/4. Okay, and again, from our binomial expansion, we go to the last term, and that 1/4 is going to be raised to the highest power. And then as we move towards the beginning, that 1/4 is now to the 4th, and then 1/4 to the 3rd, and then 1/4 squared, 1/4 to the 1st power, and then there are no 1/4s in the first term. Okay? Now, of course, all of this would have to be simplified, but I want you to understand exactly what this gives us. Okay? So let's now look at the problem. Okay? In part B. Let's look at the situation. Okay? It says in New Zealand in 1946 there were two different coins that had a value of 2 shillings. These were normal kiwis and flatback kiwis in the ratio 3:1. Okay? So the ratio 3:1 is where we got that 3/4 and 1/4. Okay? So 3/4 of them are going to be normal, 1/4 of them are flatback. Okay? Does that make sense? Does that make sense? Okay. From a very large batch, why would they say that?
Why they say what?
From a very large batch of 2 shilling coins.
It's supposed to be like you need a large number, like a really large number of like tribes.
Okay. Okay, we need a whole lot to choose from because what we're going to assume for the binomial probability distribution is that the events are independent. Okay? Now, someone explain to me what independent means.
Doesn't need something else to happen before.
Oh,
Doesn't rely on.
What?
Doesn't rely on other.
Okay, well, I mean, that's what the word means. It doesn't rely on other things. And actually, it kind of means the same thing in statistics. Matthew?
one probability isn't affected by the other. Probability.
Okay, yeah, the probability is not affected by what happened before. Okay? So if I pick a coin out, and it happens to be a normal kiwi, the next one is still going to have a 3/4 chance of being normal and 1/4 chance of being flatback. Okay? In other words, every time I pick a coin out, I'm having exactly the same probabilities. That can occur in situations that are truly independent, like flipping a coin or rolling a die. Or it can happen in things like this, where we have a statistic, like 3/4 of the coins are normal and 1/4 are flatbacks. And we're looking at a very, very large population. Okay? If I were to pick 5 of you at random, okay, and I didn't want to pick the same people at the same time, then your chances of getting picked the second time would increase if I didn't pick you the first time. Because we've only got, what, 16 people in here? 17 people? Okay? So when I take one person out of the group, there's a significant difference there. If we're talking about millions of coins here, picking 5 out is not going to change my probabilities. Okay? We're talking about, millionths of a percent. Okay? So it's not going to impact anything. So we can treat this as independent. All right, so it says we've picked 5 coins. That's why we raised this to the 5th power. Okay? Now, it says find the probability that 2 were flatbacks. So one of the things you've got to make sure you identify here is which part of the expansion is which. So the flatbacks were the 1/4 part. Okay? So those are the flatbacks. And the normal ones were the 3/4 probability. And identifying that is important here. If I want 2 flatbacks, 2 is the 1/4, so I want the term where the 1/4 is to the 2nd power. Okay? If you could get this now, it makes all of this stuff so much easier. Alright? We want 2 flatbacks, so the 1/4 has to be squared. By default then, that means we had 3 normal kiwis. Okay? So this number 1 here is going to be whatever this equals. Okay? It's that term right there. Okay? And we can go through each one like this. All right, we've got, let me get, we'll do orange for that one. At most, 3 were normal, okay? Normal are the 3/4. So at most 3. So this term that we already got, plus the one where it has 2, 1, or no normal kiwis. So that part 3 there is going to be all of these added up. Okay? And then finally, if we wanted at least 3 of them to be flatbacks, the flatbacks were the 1/4. So that means I would have either 3 or 4 or 5 flatbacks. So there, I'm dealing with these terms added together. Okay? And again, you can look at just the exponents. 3 flatbacks, the flatbacks are 1/4, so that means I have 3 or 4 or 5. So it's the 3rd, the 4th, and the 5th power terms. Okay? Now, you guys can do the calculator work to do this. All I will say is on your calculator, either use decimals, like 0.75 to the 3rd and 0.25 to the 2nd, or make sure that you put the fractions in parentheses. Okay? If you don't, it's going to mess everything up. Okay? So, now, we will learn how to do this with our calculator as well, okay, and that's where it really gets nice, okay, but I want you guys to get used to writing out the expansion and identifying the correct terms first of all. Okay? What? Okay, so you guys already came up with this by hand. Skipping back to this problem that we looked at earlier. Guys, we got all these by hand, and we identified for each of these parts of the problem what we would have to do. And even with the scientific calculator, that would be a real pain. All right? But now we're able to actually figure things out. For example, if I want at least 2 to be faulty, we said that you'd have to figure out these first 11 terms of this expansion. Okay, we highlighted it there in yellow. Well, now that we know how to use our calculator, we can simply do binomial, which one? CDF. In this case, there were 12. Our probability was 0.06. And we want it to go from no faulty ones up to, or I'm sorry, hang on, the 0.06. We want it to go from 2 faulty ones up to all 12 faulty ones. Okay?
So why don't you do up to 2 and then 1 minus that?
So we're going to do 1 minus this up to how many?
2. Oh, 1.
1.
Because it's at, yeah.
Okay? So that right there will subtract the probability of having no faulty ones or 1 faulty one, and that'll give us the probability of getting at least 2 faulty ones.
So we have to do the CDF of the 12.6 and 1 minus the CDF of 12.6, 12.
Well, 12.0612 is going to just give us 1, because that's everything, right?
Yeah.
So you're doing 1 minus.
Are we supposed to subtract the CDFs here?
In this case, you don't have to, because the 1 is just 100%.
Oh, it's cumulative, so we just plug in 1 and then get 0.84.
What do you guys get for that one?
Oh yeah,
0.16.
0.16?
Yeah,
Zero.
Okay.
Wait, do 1 minus that.
Oh, 1 minus that.
No, it's 1 minus 0.84.
Yes.
But so it equals 1.
Oh, okay. So yeah, the 0.84 you got was just this part here. That's the probability of getting no faulty ones or getting only 1 faulty one out of 12. Okay? So then you subtract that from 1, and that'll give you the probability of getting at least 2 faulty ones. Okay? Okay, if we were using sigma notation for this one, I would just do the sum from x equals 2 to 12 of the binomial PDF with 20, sorry, not 20, last problem, 12.06 and x. And that'll give me 2 to 12. So, whichever one makes most sense to you, do it that way. Okay?